Chapter 4 Higher Order Differential Equations Section 4.1 Preliminary Theory Linear Equations A homogeneous linear n-order differential equation is of the form the sum of the y and its derivatives on the left-hand side equals the right-hand side, which is 0. A non-homogeneous linear n-order differential equation is of the form the sum of the y and its derivatives on the left-hand side equals the non-zero function of the independent variable on the right-hand side. Superposition principle for homogeneous equations. Let y1, y2, all to yk be solution of the homogeneous n-order differential equation on the interval I, then the linear combination is also a solution. A concept multiple y equals c1 y1 of a solution y1 of a homogeneous linear differential equation is also a solution. A homogeneous linear differential equation always possesses a trivial solution, which is y equals 0. For example, the function y1 equals x squared and y2 equals x squared times natural log x are solutions of the homogeneous linear equations. By the superposition principle, or the linear combination y equals c1 x squared plus c2 x squared natural log x is also a solution of the equation. Linear dependence, linear independence. A set of the functions f1, f2 all the way to fn is said to be linearly dependent on an interval I if there exists constants c1, c2 all the way to cn, not all 0, such that c1, f1 plus c2, f2 all the way to cn, fn equals 0 for every x in the interval. If the set of the functions is not linearly dependent on the interval, it is said to be linearly independent. Criterion for the linearly independent solutions. Let y1, y2 all the way to yn be n solutions of the homogeneous linear n-order differential equations on the interval I, then the set of solutions is linearly independent on I if and only if the Wronskian or W of all solutions not equal to 0. And how to find the Wronskian of the solutions? We can set up the matrix, the n by n. If we have the n solutions, like f1 all the way to fn, find the Wronskian by finding the determinant of the n by n matrix. The first row has all the solutions, like f1, f2 all the way to fn. The second row for the first derivative, and then keep going with the second derivative and higher order until n minus 1 derivative. Then you will get the n by n matrix and find the determinant. If the value of the determinant is not 0, therefore, the set of the solutions, they are linearly independent. Any set y1, y2 up until yn of n linearly independent solutions of the homogeneous linear n-order differential equation is said to be a fundamental set of solutions. Let y1, y2 up until yn be a fundamental set of solutions of the homogeneous linear n-order differential equation on the interval I, then the general solution of the equation on the interval I is in the form of y equals c1 f1 plus c2 f2 plus all the way to the cn fn, where ci, I equals 1, 2, 3 up until n are arbitrary constant. Example, determine whether the given set of functions is linearly independent. To verify whether the set of the solution or the set of the functions is linearly independent or not, we check by using the Wronskian. If the Wronskian is not zero, therefore the set of the functions is linearly independent. The first example, we have two functions. Set up the Wronskian by finding the determinant of the 2 by 2. The first row would be the function f1 and f2, which is cosine of natural log x and sine of natural log x. And then the second row is the derivative of the previous row. The derivative of the cosine is negative sine of natural log x, and the derivative of the log x is 1 over x by using the chain rule. Similarly, for the second function, the derivative of the sine is cosine natural log x multiplied by the derivative of the log x, which is 1 over x. And then we find the determinant of this matrix. Multiply crossway down. We have cosine of natural log x multiplied by cosine natural log x divided by x subtracted by the product of multiply crossway up, which is negative sine of natural log x over x multiplied by sine of log x. Simplifying, we have cosine squared of natural log x divided by x plus sine squared of natural log x over x. The common factor 1 over x multiplied by the cosine squared natural log x plus sine squared of natural log x. Recall the Pythagorean identity. Cosine squared of an angle plus sine squared of an angle equals 1. Therefore, this Wronskian is 1 over x, and x cannot be 0 based on the restriction of the natural log x, so x has to be greater than 0. Therefore, the 1 over x is not equal to 0. If the Wronskian is not 0, we can say that the function f1 and f2 are linearly independent. Next example, f1 is e to the x divided by 2. f2 is x times e to the x divided by 2. From the Wronskian, W equals the determinant of the 2 by 2 matrix. The first row is the row of the function e to the x over 2, x times e to the x over 2. Find the derivative to get the second row. The first function, the derivative is e to the x over 2 multiplied by the derivative of x over 2, which is 1 over 2. And in the second function, it is in the product form. We're going to use the product rule to get e to the x over 2 plus the x times e to the x over 2 divided by 2. Find the determinant. Multiply crossway down. E to the x over 2 multiplied by e to the x over 2 plus x e to the x over 2 divided by 2. Subtracted by multiply crossway up, which is 1 over 2 e to the x over 2 times x e to the x over 2. And next, simplifying, we see the e to the x over 2, e to the x over 2 as a common factor. And then combine the groups. So e to the x over 2 plus x over 2 e x over 2 minus 1 over 2 x e to the x over 2. As we see, x over 2 e to the x over 2 will be cancelled out. And then we get e to the x over 2 times e to the x over 2, which is e to the x power. And exponential is not 0. Therefore, these two functions, f1 and f2, are linearly independent. Example 3. f1 is e to the 2x, f2 is e to the 5x, f3 is e to the x. This time we have three functions. Form the Wronskian W determinant of the 3 by 3 matrix. The first row is the functions f1, f2, and f3. Second row is a derivative of the first derivative of the function, which is 2 e to the 2x, 5 e to the 5x, and e to the x. The third row is the second derivative. We have 4 e to the 2x, 25 e to the 5x, and e to the x. To find the determinant of the 3 by 3, it can be done in different ways. You can use the cofactor, co-minor method, or you can use the way that it's called the augmented matrix by adding two more columns, which is the first two columns. E to the 2x, e to the 5x, 2 e to the 2x, 5 e to the 5x, 4 e to the 2x, 25 e to the 5x. This way is called augmented method by adding two more columns from the first two columns and then treat them like we multiply crossway down. The first one would be e to the 2x multiplied by 5 e to the 5x multiplied by e to the x, and then added by another set, which is e to the 5x times e to the x times 4 e to the 2x. Another set, e to the x, 2 e to the 2x, 25 e to the 5x. And then subtracted by the group that multiply crossway up, which is 4 e to the 2x times 5 e to the 5x times e to the x. Another set, 25 e to the 5x times e to the x times e to the 2x. And one more set, which is e to the x times 2 e to the 2x times e to the 5x. And then simplify. As we see the common factor of each term as e to the 8x. In the first group, we have 5 plus 4 plus 50 minus the second group, we get 20 plus 25 plus 2. And then simplify to be 12 e to the 8x, which is not 0. That tells us the f1, f2, f3 are linearly independent.